Okay, so good morning, welcome back. Okay, so let me first recap what we saw yesterday. So the goal is to better understand constraint optimization problems such that Hartree fork or Concham, but also Cancès CF, MCS-CF, you name it. So we focus on these two formulations of Hartree fork and Concham. The first one is a molecular orbital formulation, where the unknown is a rectangular matrix. So the rectangular matrix containing the coefficients of the molecular orbitals in the atomic orbital basis set. And this matrix C is constrained to satisfy this orthonormality constraints, the ones you have in a Hartree fork theory or Concham. And in the density matrix formulation, then the unknown is discretization of the one-body reduced density matrix. So it's a symmetric matrix, which of dimensions the size of the basis set, which satisfies this constraint, dsd equal d and trace of sd equal n. Okay, and we would like to better understand the geometry of this problem. So to do that, we first introduce Euclidean spaces. As you see, we work with matrix spaces. So as I said yesterday, it's always possible to reshuffle a matrix into a very long vector, okay? But it's not the best way to go. It's better to consider the matrix as a matrix, okay? And to see it as a point in vector space of matrices. Okay, so the frameworks, mathematical framework, the framework of Euclidean spaces, which are finite dimensional vector spaces endowed with an inner product and associated norms. And when we manipulate matrices, it's often very convenient to use a Frobenius inner product, which is defined as follows. So the Frobenius inner product of M and M prime is defined as a trace of M transpose M prime. And in fact, it's the same inner product as if you had reshuffled the matrix into a big vector, okay, a long vector, but it's much more convenient to work with that than to work with the coordinates, okay. Okay, so then we define the concept of open sets. So an open set of Euclidean space is a subset of the Euclidean space such that for each point of omega, you can find some epsilon such that, so what's that? So that's geometrically that the ball, this is my set omega, this is my point x, and this is a ball centered at x with radius epsilon, okay, like that. And what we ask for the set to be open is that for any x in the set omega, you can find some epsilon, some small radius, such that the open ball centered at x and with radius epsilon is completely included in omega. And this allows you from x to explore all the directions around x. Okay, that's because yeah, we are trying to solve optimization problems. So it's important to know in which direction you can go and stay in the minimization set. Okay. Okay. Now, if x is, I forgot to mention that yesterday, but if you have a point x in V, what we call an open neighborhood of x is simply an open set of an open subset of V containing the point x. Okay. I will use this terminology today. Okay, then we define the notion of derivative or differential. We take two Euclidean spaces, V and W, omega an open subset of V, and a function from omega into W, sorry, and some point x in omega. And we say that f is differentiable at x if there exists some linear map from V to W, such that for all h in V small enough, then f of x plus h is equal to f of x plus this term, which is linear in h, plus some reminder, which is small compared to h. Okay, and if the derivative, so this is called the derivative or the differential of f at x, And if this guy exists, then it is unique. It's very easy to see that. And most importantly, it's independent of the chosen inner product on V and W. Okay, at least in finite dimension. And here we assume that we're in finite dimension. Okay. So now we can define the gradient. If f is differentiable at x, then there exists a unique vector in V. Sorry, f has to go from omega to r. Okay. I take W. So this is for generic W. This is for W equal r. Okay. And if it is differentiable at x, so then there exists a unique vector that we denote by grad f of x in V, such that, which is, so to say, the representative of this linear form. Now this is a linear form, okay? And there exists a unique vector of V such that the derivative of f at x applied to h is equal to the grad f of x scalar h, okay? And yeah. So an important point is that this vector depends on the chosen inner product on V. Okay. So I gave you a couple of examples. So the first one is Rn endowed with the usual Euclidean inner product. In this case, the gradient is simply the well-known Euclidean gradient, that is a vector containing the partial derivative of f with respect to each variable at point x. Okay. Now, if I change the inner product, so I replace the Euclidean inner product with this inner product, which is common in quantum chemistry because S is a overlap matrix when you discretize, okay? So it makes sense sometimes to use this inner product. And in this case, the gradient of F, which I denote by grad S of F to emphasize the dependency on S, is equal to the inverse of the matrix S applied to the Euclidean gradient. Okay. And last example, if I take V, this set of rectangular matrices, and F of C is a trace of H C transpose, where this guy is a symmetric NB times NB matrix. Okay, so that's the first term of the Hartree-Fock or Kohn-Sham energy functional. Okay, when you discretize it, the linear terms, the one electron terms. And if you endow this space with the Frobenius inner product, then the gradient of F at C simply the product of H by C. Okay. And we ended up with geometrical interpretation of the gradient. So geometrically, the gradient is the vector in the space V, which points towards the steepest ascent direction of F. Okay. And I gave you the mathematical formula yesterday. And the norm of the gradient is proportional, if you want, to the slope of F in this direction. Okay. And as soon as you have understood this interpretation, yes.
Yeah, a little question about this.
Yeah, sure.
The gradient. If you go to the infinite dimensional
yeah.
space, it generalizes to integral.
Okay. Okay. Yes, a good point. So what's going on if V is infinite dimensional? So first, you need some completeness. You need a Hilbert space. Okay. So if you have a Hilbert space, then if F is differentiable, the gradient is unique, and it depends on your representation of it depends on the Hilbert space. So for instance, if you take V equal L2 of R3, say, for instance, okay, and with real value functions. And if you take F of, let's say, V equal the integral on R3 of some function, which I call, let's say, capital F times V, okay, where F is a function in L2, then the gradient of F at V is in fact constant and it's equal to F. Okay, that's an example. So it doesn't need to be an integral. It can be an integral. For instance, if here you have something, well, there's, yeah, depends on the function and it depends on the representation of the infinite dimension. So but another case of infinite dimensional case is the set of sequences, okay, that you find in Fourier representations, for instance, okay. Well, in this case, the gradient is just a sequence, okay. So it really depends on the, but what is important, it's always a vector of the space you work in, okay. If you work in space of functions, it will be a function. If you work in a space of sequences, infinite sequences will be a sequence. So always, yeah. And so what is good is that when you understand that, then you can understand the meaning of the steepest descent algorithm. It just as you construct a sequence, you start from initial guess x naught, 1 minute, Salma. Yeah. And then you iterate. So for instance, if at iteration k, I'm here, I compute the gradient at iteration k. I know that if I go this way, the value of the function increases. So I go in the opposite way. I'm sure that locally the function will decrease. And so I will make a small step t in the direction opposite to the gradient. And I will define xk plus 1 as xk minus t, so the step I do, but times gradient of f at xk, okay? And I can do that because these two guys live in the same space, and so I can add them up, okay? I can do linear combination of both. That's why I really need a gradient, okay? Okay? Right. And then I think Antoine will show you that under some assumptions on f, if t is small enough, then this algorithm actually converges. It's probably not the most efficient, that's for sure, but okay, it works, the starting point. Salma, you have a question? Yeah. Good point. Okay, so it's because, so what is the steepened ascent direction? So as I defined it yesterday, the direction of the gradient. So that is this, of course, if the gradient is zero, it's zero. Okay. But if it's not zero, this is the arcmax. So it's so what is the arcmax? When you have a minimization problem, the arcmax or maximization problem, the arcmax is the set of maximizers. Okay. And I define this problem as so df of v with v in v with norm 1. Okay, and it's there that there is okay, the choice of the inner product. If you change the inner product, you change the norm, and so the vectors do not have the same length. Okay, and so yeah, that's yeah. No, it's really for the gradient. Well, yeah, the derivative it's a linear map from, well, the interpretation, it's more that. It's the way, it's the first order variation of f when you make a step h. Okay, so you are at x, you change a little bit, you move a little bit by h, and at first order, the variation of f is the derivative of f applied to h. Okay, so if v is Rn, so if this one is in Rn, and if this is in Rm, okay, that is v equal Rm and w equal Rn, then this is a vector of Rn, and this is a matrix with m rows and n columns, which contains the first order derivative of each component of f with respect to xi. Okay, yes?
Is it necessary to give a more precise definition of small?
No, well, this can be given a very precise mathematical. I don't want to do that, but because it's yeah, but yeah.
No, can there be some traps when you don't take care.
No,
of it.
small means.
That's what it's an H square.
Okay, no, yeah. So basically the meaning of that is that if you consider this, okay, you consider this, you divide by the norm of H, and this goes to 0 when H goes to 0. Okay, that's the definition of the little o. Okay. Yes?
So you said that the way it depends on the norm, I mean, on the inner product is on the norm.
And therefore, yes?
But so it's only the scale of the vector that
Yeah.
will change, but not the direction.
No. The direction will change because if you go, you want to, so you are at point X, you make you make a change because okay, maybe it's better if you say that and assume that t is small. Okay, it's just linear. Okay, so I can do that. Okay. But now this, if t is very small, this is a small vector. Okay, so that's the variation of x of f if I take a step t in the direction v. Okay, but you see that if so for instance, if I take the Euclidean norm, this is this set of vectors. Okay, you can go this way or that way and so on. Okay. But now, if I take another norm with an S, for instance, if my S matrix in L2, in R2 is 10 to the 8 and 1. Okay? Then my, or 10 to the minus. Okay? So how does this look like? It looks like, well, this set with S looks like more, I don't know, something very, very, okay, something like that. Okay, and so it's completely biased by the direction you go in. So if you change the inner product, you change this picture, and therefore it's different. Okay. Any other question? Yes.
The question is maybe you're going to talk about it later, so
Okay.
So
okay.
so when you talk about like changing the metric of
Yeah.
gradient and so on, let's say you have the matrix C where you have the coefficients.
Yes.
And you compute the derivative of the gradient.
Yes. Okay. Whatever.
And so you do like a steepest descent kind of algorithm.
Then I need the gradient to
Okay,
do steepest descent. Yes.
So you're going to rotate your orbital, but you might end up with a set that is not, for example, orthogonal anymore.
Of course, yeah, because I'm not working so this is a picture when I minimize over a linear space, a vector space. Okay, here I minimize over something which is a curve on a manifold, and then of course you have to adapt that. I will talk about that. Yes.
Steps so that
Yeah. So I will talk about that. Yeah, indeed. Yeah, maybe not today, but tomorrow. But yeah, I'll talk about that. Okay. Other questions? Good. Okay. So now I need to introduce another concept. Which is the notion of CK diffeomorphism. This sounds scary, but it's something you are used to in some way. So what's that? Okay, I take V W Euclidean spaces. Omega 1, or say V1, V2, sorry, V1, V2. V1, V2 Euclidean spaces, omega 1 included in V1 open, and omega 2 included in V2 also open. And then F or phi, yeah, what F, phi from omega 1 to omega 2. Okay. So phi is called CK diffeomorphism. If, so first, phi is invertible. And second, phi and phi minus 1, so the inverse of phi, are of class CK. So what's that? Class CK means that have continuous derivatives up to order K. Okay, meaning that you can compute the first, second. So if phi is a C3 diffeomorphism, it means that phi and you can compute the first, second, and third derivative of phi, and that these functions are continuous. And same for the inverse. Okay. We'll see examples later on. Alors, remarque. If phi is a diffeomorphism, is a CK diffeomorphism, then V1, then sorry, d phi of x. So this is a map from V1 and V2, and d phi of y from, or let's say x1 and x2, from V2 to V1 are invertible for all x1 in omega 1, x2 in omega 2. This is very easy to see. Take x1 in V1 and x2 in sorry, in omega 1 and x2 equal phi of x1, which is in omega 2. And then I apply the chain rule to the relation that x is equal to phi of phi minus 1 of x. Okay. And if I apply the chain rule to that, or maybe I can go the other way. So what you have through the chain rule, you that's the identity. When I differentiate that, I get the identity. So this is, so here I work in omega 1. So this is the identity of the space V1, and this is the derivative of phi, minus 1 at point phi of x1, so this is x2, and multiply by the derivative of phi at x1. Okay. And so this means that, and the same for you also have that. And so they are invertible. Yes?
Just notation. When you said then D5 from G1, like the second line.
Yes, this.
Then third line, there is minus 1.
Sorry, yes, thank you. Yeah, thank you, of course, thank you. Okay, and so a consequence of that is that necessarily the dimension of V1 is equal to the dimension of V2. Otherwise, you cannot have this invertibility. Okay. So in particular, the dimension of V1 must be equal to the dimension of V2. Okay, so that's all I wanted to say about differential calculus. Okay, now we have the tools to move to manifolds, so curved spaces. So this number is what? Yeah. Okay, so I call that 2, which is the geometrical viewpoint. And so what is the idea? So the idea is to rewrite the constraint, the equality constraint optimization problem as the infimum of some function f over m, and m will be a smooth Riemannian manifold. Of course, I will define what this is. Okay, and once you have that, then basically you can translate all you do in linear vector spaces to manifolds. Okay, in the sense that we will have a very simple interpretations of the critical points. Okay, or the notion of critical points or stationary points, and we will see how to transpose the idea of steepest descent algorithm and more advanced direct minimization algorithms to Riemannian manifolds. Okay. But of course, for that, I need to define what is a Riemannian manifold. And so I will go slowly because it's perhaps it's the first time you see that it's not obvious. So please ask questions. So section 2.1 is what I call the survival kit of differential geometry. Okay. And yeah, so one disclaimer first, we will focus on smooth submanifolds of Euclidean spaces. So I will not describe manifolds in general because to avoid some technicalities, I will assume that my curve space, my submanifold, is embedded in a Euclidean space. Okay. And to start with, I will start with the first example, which is the usual 2D sphere. So that's a manifold you know very well. That's that, okay? So how do you to describe this object? So, well, first you can see that locally this looks like a two-dimensional space. Okay, at the point that some people believe that the Earth is flat. Okay, so it's really locally it's really. So how do you mathematize that? So for that, so let me write that the 2D sphere. So the 2D sphere is S2, okay, it's the set of vectors in R3 such that the Euclidean norm of X is equal to 1, okay? So locally, S2 looks like a 2D vector space. And so to give that a rigorous mathematical meaning, I will rely on the concept of CK diffeomorphism. Okay, so what do I proceed? And so at each X, for each X in these two, we can find so an open neighborhood of X in R3. Okay, open neighborhood means an open set containing X. Real number eta positive, and a C infinity diffeomorphism I call psi X. Going to, I need to give a name to this guy, so omega X, which goes from omega X to minus eta to the cube, such that psi X of omega X, the intersection of omega X and so the manifold, I will call it, yeah, okay, and S2 is exactly minus eta square times 0. Or in other words, psi X of minus eta square times 0 equal omega X, psi X minus 1, sorry, is equal to omega X inter. Okay, so let me draw, explain what this means. So it means that locally, so you take a point, you pick a point, let's say X here, okay, and then you have you are in the three-dimensional space, and then you have a cube. Should have hired someone to draw. Eloise, are you okay? Want to come? Oops. Okay, something like that. So that's the cube. That's the cube minus eta to the cube. Okay, and then there is a mapping. So this is psi X, and this is psi X minus 1, which transforms this cube. So psi X minus 1 transforms this cube into something which looks like a curved cube, if you want. Let me, okay, something maybe like that. Okay, something like that. And such that when you transform, so the cube maps to the cube, but if you just apply the psi x minus 1 to this set, to this square, you get the intersection of this omega x here with the sphere. Okay? Right? What do you gain? You gain that now every point in this local patch on the sphere correspond to a point in the R2 space, okay? Because here you have two coordinates. Let's call them S1 and S2, for instance. And here I can represent locally my sphere by just two coordinates, S1, S2, okay? And so now I'm back to a vector space. Oui?
So basically, you take a small curved area of the sphere and you flatten it into a...
Yes, kind of. Yeah, the way, yeah, exactly. And the way to flatten it is this through this diffeomorphism. Okay, but instead I take more than just yeah. Okay, I take a neighborhood of that. And, yeah, but yes, basically yes. Yeah. On the sphere, is on the sphere. Is the intersection of omega x with the sphere. It's just that my drawing abilities are very poor, but okay, yes, that's the idea. Okay, this is yeah, and there is a one-to-one correspondence between the orange set here and the orange set there. Okay, yes.
And the yellow cube is like a cube orthogonal.
No. It's not. It's a deformed cube. It can be something. Yeah. But it's but it has it's a deformed cube through a C infinity diffeomorphism. So you cannot. You still have a kind of sharp angles. Okay, yeah, you cannot do, yeah. So like, I can choose the cube. Yeah, I could choose a cube. But yeah, I can design psi x. I can design psi x so that I have a cube here, if it is what you mean. Okay, but this is more general. Okay, but yes. But I can do that here, but when I manipulate some, yeah. Yeah. But yes, you're absolutely right. In this particular case, I can do that, yeah. Okay, yes? Oh, it's, yeah, it's an open cube. Yes, absolutely. It's an open cube, but a cube I didn't, but you're right. Okay, it's an open cube, but I mean, it's up to me to define. Like you can take, you can consider the open ball or the closed ball. Here I consider the open. This is also a ball, but for the L infinity norm. Okay. Yes. No, you can, because if you have an open set, you can talk of its boundary, and yeah, you could, but yes, but yeah. Okay. All right. So now I can define two more things. So now, once you have that, you can define Px, which goes from omega x intersection S2 to minus eta to the square, defined by well, simply that psi x of psi x of x, sorry, psi x of x prime for all x prime in omega x 2 equal phi x of x prime 0. Okay, so I just take the first two coordinates of the map psi x. Okay, because I know that if this point belongs to this set, then here I have 0. The coordinate is 0. So I just consider the map. And this is called a local chart. S2 at x. And it's inverse. So its inverse goes from minus eta to omega x x2. And this is called a local system of coordinates. Okay. Then we'll see later that, for instance, what you say, the Grassmann manifold, the Stephan manifold, can be parameterized like that by a system of coordinate, and then you back to the flat space setting. Huh? Okay. Manu, no, you're processing. Okay, good. All right. Okay, now I can define another thing. Yes? This? Yeah. So what is more important is phi x minus 1, in fact. Okay. And this one is a mapping. So phi x. So you are in two. So you are in 2D. So it's a map from this square, which is a flat square, to this portion of sphere, which is defined by omega, the intersection of omega x with a sphere. Okay, and so it's really something like that. Huh? It's really a map. This you go, you have something which is flat, okay, and this is a map of the Earth. So this guy is a map which associates to a point in my map here, a point in on the manifold.
My question is,
yes, phi goes from 2D to 2D. Psi goes from 3D to 3D. Yeah.
So the tensor that they define in the general relativity.
Yes.
Is it this type of transformation?
Well, the thing is that yes, kind of, in the sense that in general relativity, you don't assume that the time space is embedded in a manifold of higher dimension. You work, so that's why here I'm sticking to the framework of submanifolds. In general relativity, you don't embed. Well, there is a theorem, Whitney theorem, which tells you that if you have a d-dimensional manifold, you can always embed it in a 2D dimensional flat space. Okay, but usually it's not the right way to go. Okay, in general relativity, you don't embed your 4-dimensional space into an 8-dimensional space. Okay, nobody does that. Okay, you could, but you work directly with a curve to a 4-dimensional space. Okay. Yes?
In the case of the sphere,
yeah.
Is there a link between this local coordinate system and just the spherical coordinates?
Yeah, okay, let's do that. Yeah, good point. Okay, so let's illustrate that using the spherical coordinate system. So what would you do? So example. So I take again my sphere, and I consider one point of the sphere, x, which is of with spherical coordinates. So let's call it theta naught, okay, and phi naught. Well, little phi naught, okay. And you know that x. So So let me call it x naught, okay? So I'm focusing on the point x naught. So x naught, the coordinates of x naught are just, so it's a sphere of radius 1. So it's just sine of theta naught cos phi naught, sine of theta naught sine phi naught, and cosine of theta naught. Okay, that's a radius 1, yes, S is written somewhere there. Okay, so now if I want to construct some psi, well, actually what I will do is to construct psi x naught minus 1. I will take a small eta, so it's I will map this to R3. Okay, well, actually to well, some omega x and S2. No, sorry, some omega x. And what is omega x naught? So I take so something which will play the role of theta. So let's call it small theta. Yeah, theta. Okay, theta. Theta tilde, phi tilde, and r. And then I will define the coordinates. So this will be 1 plus r, or r tilde. 1 plus r tilde sine theta naught plus theta tilde cosine phi naught plus phi tilde. 1 plus r tilde sine theta naught plus theta tilde sine phi naught plus phi tilde. And 1 plus r tilde cosine of phi naught plus phi tilde. Theta naught plus theta tilde. Okay? And you can check that this is exactly what we have, because if we apply that to theta tilde, phi tilde, and 0, okay, then I find a point on the sphere. And when you let theta tilde and phi tilde span this set for eta small enough, you find it's a patch of the sphere, okay, centered at x naught. Okay, so that's a way to relate this formalism to spherical coordinates. And you can choose, of course, any psi naught to do that. And in fact, you can well, so I didn't introduce that, but what is an atlas of the sphere or the manifold? It's a set of local charts which cover the whole sphere. Okay, it's called an atlas. Okay, and to be sure to explore everything, every point in the sphere, you need an atlas. Sometimes with more than one map. Okay, for the sphere, for instance, it's not possible to define to completely cover the sphere with only one chart. Okay, it's not possible. For other manifold, it's possible, but for this one, it's not possible. Okay.
What are the problems with one chart?
With one chart is that you have so it's related to the topology of the sphere. It's not possible to cover. So it's a theorem.
Right. But the spherical coordinate system covers the entire sphere, and what's wrong with?
No, it does not, because the spherical coordinate system, you don't get this point and that point, nor the well, it depends on how you choose phi naught, but because this point you would have it's not 1-to-1. Okay, if you take the north pole of the south pole, then any phi is okay, and this is not allowed because you want something 1-to-1. Okay. And so you need more than one chart to cover the whole sphere. Yes?
And I think this is related to the argument that eta should be small enough. And how do you know if eta should be small enough to be able to?
Oh, well, here you just do the map. You check when this is invertible as no.
In the case where you can have an atlas that is only consists of only one local chart.
Yeah.
The opposite.
Yeah. So let me give you an example.
Eta can be any number.
eta is
It doesn't have to be
eta does not need to be small. No, of course. Yeah, you're right. You're right.
We must have eta at least.
Yes,
Okay.
yes, exactly.
And how do you?
Yeah.
How do you know that?
Yeah, here I said a real number. Okay. Well, actually, if you just have one, yeah, no, I think that's okay. Yeah. Sorry.
Yeah, how can you know if there is a one-to-one map between you? I mean, this-
In the general case.
Yeah, in the general case, I agree that eta should be small enough. But
Well, not necessarily, because you can always rescale things. You can always rescale that. Okay, so if you have a map of size eta, you find a map of size I don't know 10 times eta by just scaling everything by a factor 10. Okay, so the magnitude of eta is not very relevant. And even if you have the full space, which is infinite, you can have a scale which function which blows up at infinity, and so it allows you to represent the full hard R to the n space with a map in -1, okay, to the n.
Is more defined the open neighborhood than the manifold.
Yeah.
And that's your
Right.
open neighborhood plane, that's
Yeah.
that's arbitrary difficult.
Exactly. And so you usually, yes, that's a very good point.
one point of the sphere.
Yeah, you can have a chart which covers the whole sphere but a point. That's possible. Yes. Yeah. That's what you get, for instance, with the Mercator projection and so on. Okay. So not the Mercator, the one where you project, like that. Serographic. Thank you. Serographic projection. Yes. Okay. Yes.
Just to be sure, so here, this cube of length theta, this means that both theta tilde, phi tilde, and r tilde, they can go from minus theta to theta.
Yes, exactly. Yeah. So it's like you are on a vector space. This is what is nice with this description.
And the last question, so here you define psi minus 1. Okay.
Yeah.
But so, to be sure, the phi.
Okay, yeah. So the phi x naught and -1, the local system of coordinates, is just minus eta to the square 2 omega s naught intersection of S2, and which associate to theta tilde phi tilde the same formula, but with r tilde equal 0. Okay. And so on.
Are there some theorems that say like, okay, what's the minimal number of maps in the atlas?
Yes.
And,
Yes, it
but
depends
I'm
for
wondering-
two-dimensional surfaces, for instance, it depends on the genius of
okay, so there are some
they are characteristics. Yes.
But a second question is it even important, because formalism probably is not
No.
Dependent on how many maps, right? So
Well, locally, no. Globally, yes, because here we are only talking about local properties, because we are doing optimization. But if you think in terms of, for instance, of there are other cases where it's very important to consider the full geometry, the topology, let's say, of the manifold. And in this case, the topology is something global. And for instance,
but I was wondering, is like, if the minimal number of maps is say 2,
yeah,
and then you use 3, that's still fine, right? Because there is
yeah, absolutely.
The formula is
No, absolutely. And you can. There is a maximum atlas containing all the possible maps. Okay, that's a mathematical object, mathematical chart. All the local charts. That's fine. As soon as you are, yeah, absolutely, yeah. Yes.
Another question. Sometimes people are using these redundant coordinates to avoid this problem of they are defined in one place, not in another.
Yeah.
is it equivalent to embed the manifold maybe in a larger dimension space?
The thing is that if you do that, you don't have a one-to-one correspondence. Maybe it's not, it depends on what you do, what you want to do with that, okay? Sometimes it's fine. We will see examples where it's perfectly fine to have a non-redundant parameterization, but in other cases, it's important to have a one-to-one correspondence. Yeah. Okay, good. So now one more thing about the sphere before moving on to general submanifolds. So you all know what is a tangent space 2S2. In fact, it's a tangent plane 2S2 at some x in S2. Okay. This is called Tx S2, the tangent plane at x. Okay. So we will, so it's a set of vectors which are like that. Okay. So when you have this picture, it's quite easy to understand what is a tangent plane. But now you would like to find a way to characterize the tangent plane, or in general the tangent space, which is intrinsic to the manifold. Okay. So to do that, the way to define it is the following. What you observe is that if you draw a smooth path on the sphere, then, okay, so what is a smooth path? A smooth path is a path from minus tau to tau in R3 of class, well, C1 or well, it doesn't matter. Let's say C infinity, but it doesn't matter. Okay, and which T associate some phi of T. So it's a trajectory if you want, okay? It's a trajectory. And you will impose that for all T in minus tau, phi of T is on the sphere. And then you will impose as well that phi at point 0 is at the point you are interested in. So here, x. Okay. So this is called a smooth path on the sphere. Okay. And you can define the tangent space as the set of V such that there exists a smooth path P on the sphere such that phi dot at 0, so this is the first derivative with respect to time at t equals 0, is equal to V. Okay. So way to characterize the tangent space, tangent plane. Okay. And indeed, so here, well, is it clear that that this gives you the tangent plane, or do you want me to elaborate on that? Yes, I can. You mean? Yeah, I can. Okay, so let's do the following. So first, what is the tangent space to S2? Okay, so the tangent space to S2, you can see the set of vectors which are here orthogonal to X. Okay, so it's the set of V in R3 such that X dot V equals 0. Okay, that's tangent plane. Okay. Now you can see that if sorry, and yeah, here I put phi of just to be sure. Okay, it's already here, but okay. Well, okay. Let's say that this is okay. Sorry, this is a smooth mass on the sphere, and I impose that the smooth path is at x at t equals 0, and its derivative is v. Okay, it's better to go this way. Okay. So if phi is a path on the sphere such that phi of 0 equal x, phi dot 0 equal v, then, well, it's clear that you have phi of t is equal to 1 all the time. I can put a square if I want, okay, because it's a point in the sphere. So its norm, the square of this norm is equal to 1 for all t, okay? And then I expand that, I do Taylor expansion. I have phi at 0 is x, plus t phi prime or phi dot at 0 is v, plus a little o of t. Okay, I expand that. I find the modulus of x squared, which is 1, because x is on the sphere, plus 2t x dot v, plus little o of t. And this is correct for all t small enough, okay? And then I get rid of the 1, and I find that this is valid for all t small enough, and so this gives me that x t has to be equal to 0, okay? And so this tells me that V is, so now I have two definitions of the, so this is definition 1. So this is okay, this is the definition 1, this is definition 2 if you want, okay? I want to prove that these are the same, okay? So I take a V in 2, and I just show that this is a V in 1, okay? So it means that if I have 2, I have 1. 2 is included in 1, okay? So to say, okay? All right. And conversely, now I take a point in 1, and I have to find a path on the sphere satisfying that, okay? So if V satisfies, so that's conversely, if V satisfies x dot V equals 0, then I can find a path on the sphere, and it's quite easy. What I can do is that x plus TV divided by x plus TV. Okay, so it's clear that this is a path on the sphere. If t is small enough, this is non-zero. Okay, so it's a smooth path for t small enough. It is on the sphere, and when I differentiate, I have phi of 0 equal x, and if I differentiate that, that you will find that phi naught of 0 equal v. Okay, and therefore 1 is included in 2. And so the two sets are equal. Yes?
How do you know that x plus TV is on the sphere?
X plus TV is not on the sphere, but when I divide by the norm, here I divide on the norm. So then it's on the sphere. Yeah. Okay? Okay, so what is nice in this formulation is because then there is a very natural extension to a generic manifold, okay? Because I will take my manifold, I will draw paths on the manifold, okay? And I will characterize the tangent space as the derivative, the velocity vectors, if you want, on of the paths that I can draw on the manifold, okay?
It's still a subspace of the.
Yeah,
um,
yeah. Yeah, but it's a two-dimensional subspace. It's a two-dimensional subspace, so that's what is important, in fact. Yeah, so that's a good point. If I'm talking about submanifold, the tangent space is a subspace, a linear subspace of of the Euclidean spaces the manifold is embedded in. If I'm dealing with manifold, then I can define a tangent space which is not embedded in anything, it's just a tangent space, and it's defined something, it's equivalence classes of the derivatives of the path. I can there is an intrinsic definition without embedding the manifold.
Sometimes I've seen the definition where the tangent space is defined as operators acting on functions.
Absolutely, yeah, you can do that as well, but I didn't want to do that because it's more abstract, so to say. But yes, indeed, you can see, in fact, a vector as a differential. So the idea is to mimic directional derivatives, in fact. Okay, what you do is that yeah, you define if you are in a flat space, it is what you call the df over dv sometimes. Okay, and so if you have a vector field, you can define the equivalent of that on a manifold, and then you can define by duality a vector field as something which acts on the C infinity functions or on the sphere. Yeah, but I don't want to go into that because it's too it's a bit abstract. Okay, while here, I mean, at least for the sphere, you see what's going on. Okay. Okay, so yeah, so now it's time to go to give you the definition of a smooth manifold. So now the ground is prepared. So the definition. Let V be Euclidean space. Of dimension n, and M a subset of V. So M is called a smooth submanifold of V if for all x in M there exists. So it's really a copy paste on the first definition. Sorry, here we put a d-dimensional smooth submanifold of V if for all x there exists. So an open neighborhood of X in V, a real number eta positive, and a C infinity diffeomorphism psi x, keeps the same notation, going from omega x to minus eta to the n, such that psi x of omega x cap m is equal to, so minus eta to the d times 0, and this is the vector of n minus d. That's it. Okay. And now, so phi x, so I don't redefine phi x, but it's as previously, okay? It's called a local chart. I don't write the definition again because it's exactly the same. And phi x minus 1 is a local system of coordinates. Yeah.
Is there an intuition for why so much smoothness?
No, well, it's because when you are smooth, you can do whatever you want, okay? You can differentiate as many times as you want. There is, of course, a theory of C1 manifold or CK manifold or yeah, you don't need, but usually in standard differential calculus, you talk about you talk about smooth submanifolds. Yeah. Okay, and then so we can define the tangent space to M at X, and that's TXM is the set of vectors V such that there exists a smooth path T minus tau tau to V on the sphere. That is phi of T is on the sphere, on the manifold, on M. That is phi of T is in M for all T, such that phi of 0 equal X, and phi dot of 0 equal V. And the theorem, saying that TXM is a d-dimensional linear subspace of V. And you also have that you can find it by, so what you do is that you take the map psi x minus 1, you differentiate it at point 0, and you apply it to vectors of this form. Yep. Here. Yeah. No. That's just for the sphere. Yeah. Here, it was just to illustrate that this standard definition is agrees with this one. But now, in the general case, a good one is that one. Yeah.
Theorem is to say that once that you have defined this tangent space, just like you did,
Yeah.
you are sure that it is a d-dimensional vector space.
Yeah.
But what is written just below?
This.
Yes.
This is a characterization of it. It's how to obtain it if you know psi x. If you have some phi x, if you have one, you can compute the tangent space. Okay, which can be convenient in some cases. But sometimes you just need to know the. Well, I will show you an example, a special case of manifolds where the characterization is much simpler than this one. Okay, we'll get to that when I'm supposed to stop, Julia.
In 5 minutes.
In 5 minutes, okay. So this is what I can do. No, but that's fine. I don't want to do it. So I will maybe talk about differential calculus of manifolds. No, just one remark before that. Tm, which is the union of all the Txm, can be identified with a smooth submanifold of V times dV called a smooth 2D dimensional, a smooth 2D dimensional manifold of V called the tangent bundle. Okay, I will use it just once, but okay. And now I can talk about a differential calculus on manifold. Yep.
The tangents are all union.
Yeah. Yeah, it's a union. Well, at the beginning, it's just a set. Okay, this is a set. It's a union of all these. Like you take the sphere, and you take the union of all these planes. So it looks like a big mess. Okay, the union of all these planes. Don't. What? No, it's a union. Well, yeah, it's a union of vector. No, it's because it's this plane, and then you have this plane, and then you have this plane. Yeah, so yeah, okay, right. Yeah, it's a disjoint union, absolutely. Yeah. Oh, yeah. Okay, I see. Yeah, like that, maybe. Yeah. Okay, so disjoint union of all this, and this can be identified with a manifold of dimension 2D. Yeah, well, yeah. This is a. Yeah, there is a canonical projection from this to there is something P. which to some guy here associated, it's but let's say, okay, let me get, it's a disjoint union. So let me get a guy in there. So he's in one of these guys, the guy in which is the X. No, but here you think in terms of embedded, okay? Forget about that. It's just the union, the disjoint union, thank you, Marie, of these spaces. And then in there, you can equip that with some with
Bundle is still a subset of V.
you shouldn't see that like that.
It's a subset, but it's better to see.
Yeah. So here you define the disjoint union. So it's yes, yeah. You shouldn't. Yes, exactly. You shouldn't see that. Actually, yeah, a guy in there should be thought in terms of the point. Let me draw the sphere again, or not a sphere, something different, something like that. So a point in there should be thought as a pair of the point to which it is attached, okay, and then the vector. So it's the point to which it is attached and the vector, okay? And there is a canonical mapping. Let's say, yeah, you can think like that, okay? That's the point to which it is attached, and this guy is in TXM. Yes? Because you have it's a position and velocity basically, yeah, and it's exactly that in Lagrangian mechanics. You work, the Lagrangian is defined, so don't mess up. Okay, it's not the same Lagrangian as the one we are talking about, but the Lagrangian in classical mechanics or even quantum mechanics, but the Lagrangian in classical mechanics is a function defined on the tangent bundle to R. Okay, and if you work on I don't know dynamics on of the double pendulum, for instance, we have like that a double pendulum. Okay, to describe this dynamics. Okay, you work in a manifold in the tangent space in the tangent bundle of the manifold. Okay, so the manifold is called the configuration space, if you want, and then the tangent bundle is called well, no, the yeah, and so the phase space is the other one. The phase space is this one. Yeah, that's the cotangent bundle. Okay, this one is position velocity, and the other one is position momentum. Okay, yeah. The tangent bundle, and then there is a cotangent bundle. So the Lagrangian formalism is in the tangent bundle, Hamiltonian formalism is in the cotangent bundle. But okay, so I have to stop. Okay, so thank you for your attention.
Some of the practical questions in this gradient optimization, whether we have multiple minima or